share screen stuff. Let's see. I just came from a class, and granted, like, the professor is kind of old, so he's not very tech savvy, but he was having a lot of issues with PowerPoint and it started freaking me out. So I'm really hoping that this works out. First off, I can't hear your guys' reactions, so I'm just going to assume that everyone's hysterically laughing at all of these. But I like to do 3 gifts, memes, or dad jokes of the week because they're completely necessary for our happiness and well-being. Let's see. This is my first one. Tried to catch fog yesterday. Missed. I thought it was cute. Plus dogs. Dogs are fun to look at. I posted this one on my Instagram. I think it's pretty relatable to most people. 2020 has created its own difficulty level. Most people laughed at it. I cried. And then also, just be sure if you guys go outside, make sure that you're practicing good COVID, I don't know, coffee filters. Make sure you wear your masks. Social distancing is good, okay? I know we're like 20 and want to live life to the fullest, but be safe while you do it. All right, well, those are all I have. So hopefully that gave some light to your day. But without further ado, we are going to talk about measurements. That's kind of like the main concept of today, and then we'll kind of go into design of research and things to be cautious about when we're either reading research or conducting it. Okay, well, the first question I always pose to this class is, why do you care? And I think a lot of people in this class, it's like a requirement for your major. So you're like, well, I'm just here because I have to be. So I'm going to launch a poll, and I want you guys, it should pop up somewhere for you. I'm going to insert it into the area that is being shown right now. But I just want to know, like, what are your guys' goals? What do you want to do with your degree in the end, right? And then we'll kind of tie back how this is applicable to you, because in the end, that's what really matters, right? Lots of physical therapy. I expected that. I too once wanted to do physical therapy, and I'm clearly not doing that now. But good for you guys. Looks like pretty much everyone has participated. Some people personal training and fitness, one person in research. Woo woo. So this class is very applicable to you. Anyone who put other, you want to shout out like what your occupational goals are? You don't have to. I'm not putting you on the spot, but option to participate if you want to. Let's see, maybe it's in the chat. Ooh, nice. Okay. That's different from other students that I've had in the class. I think actually one person went on to be an EMT, so good for you. So this would also be applicable to you. Point being, you are all here for a reason. Why does this hate me? Okay. So whether you're going into conducting research, if you're teaching, if you want to go into corporate wellness, fitness, personal training, any of the therapies, right? Even if you don't know what you want to do with your life yet, which is totally fine, because I didn't even decide where I was going until literally my last semester of my undergrad. So, if you don't know what you want to do yet, that's acceptable. You have time, you're youthful. So this class is going to hopefully benefit everybody here. Reasons why is, if you're going into any type of therapy or teaching, right, you need to make sure the things that you are applying to your practice are up to date, right? And a lot of times that involves reading literature and research that is out in the world. So whether, your takeaway from this class is how to conduct statistical tests or not, you'll at least be able to know how to interpret, right, the literature that you end up reading down the road that you end up traveling, right? And you'll be able to understand how people conducted the tests that they did, why they did it, how they set up their study design, and if the statistics that they calculated actually answered the research question they were trying to pose in the beginning. Okay, so if you go into the class with the mentality that you're going to learn something that will benefit your future, I usually feel like you have a bigger or better vested interest in the actual content that we learn. Okay, well, the first thing we're going to talk about is measurements. It's kind of the base of statistics because what we're primarily going to be working with is data sets. So the big question is, how do we get those data sets? So the first thing we look at is who is measured. Now, from the larger picture, that's usually in reference to the population, which is a group of persons or people, places, objects, etc., that have at least one common characteristic. And usually for statistical calculations, we refer to stats for populations as parameters. Okay, P and P. That's kind of how I remembered it. Okay. Now, it's not always feasible to actually collect an entire population. So more often than not, you're going to be collecting or investigating a sample. And when we look at statistical calculations for samples, we call it statistics, S and S. What? So crazy, so easy to remember, okay? So a sample is just a portion or fraction of the population, right? And the whole point of statistics is that we are able to infer, right, information we get from the sample onto the population so that we can generally better understand how the population works, what interventions are going to be effective, etc., okay, or whatever variables we're manipulating. Okay, but a lot of times we have to, and this is a really important highlight, is that we need to, actually, hold on a second. I just remembered. Did I start recording this? Yeah, we're good. Okay. I got scared for a minute. But the main thing that we need to make sure of when we collect samples is that it is actually representative of the population. And the way that we do that is through random sampling. I'm sure some of you have heard of this before, right? But it basically means that every member in the given population that you're interested in researching has an equal chance of being selected to be in that sample. So a lot of times when we are doing projects in like the kin department or research projects, we'll post a flyer, and whoever sees the flyer can reach out to whoever's conducting the research and says, I want to be in this project. So the distribution of a flyer, anyone who sees it has, or in that given population has a chance to participate. The other reason why we need random samples is because pretty much every formula or calculation that is used within statistical softwares are based on the assumption that you have a random sample. Okay. Also, this helps to eliminate any bias within your recruitment process, right? So you can't just hand select people who you think are going to be fantastic, or like, you have jumping experience and you're a really good jumper, so I'm going to have you be in my vertical jump study, So randomness is good. Additionally, we can have stratified samples, right? Still random, but you're looking at subcategories of the population instead of a more general sense of a sample of your population. So example would be if you were looking at the rate of library visitation, right, in college-age females from Long Beach State, according to their major. So you could sit at the entrance of the library and You know, for every female that comes through, you could just say like, hey, what major are you in? I'm like, you know, doing a study and I wanted to, you know, take down some data. And if they consent to participate, right, you can stratify your sample based on subcategories. Okay, but random samples is like a big takeaway. This is the, well, with the exception of another assumption, it is like the main assumption that you're going to have for any statistical test you run in this class. Okay, so once we have collected the people we are measuring, we can actually collect data and make measurements, right? It's a process of comparing a value to a standard unit. That's the definition that the book gives. Basically, this just means like a value being numerical, right? So if I'm measuring vertical jump distance, right, my value, let's say someone jumps 20 inches, the value is 20, right? And the unit is inches. So measurement just combines some numerical value with some unit of measurement, right? There's two different types of measurement. We have qualitative measurement, which is more subjective because it requires the use of human judgment. And then we also have quantitative measurement, which is more objective because it uses external tools or equipment to take down the measurements, right, or measure certain quantities. So if we're measuring distance, usually we use some type of ruler, right, or measuring tape. If we're doing force, we have a force plate that collects the data for us. If we're doing time, we've got a stopwatch, right? Frequency we can count, right? There's a standardized way that we are actually collecting the quantities that we are measuring, okay? Or the ways that we get our measurements are through tests, right? So tests couldn't include any of the following: instrument, tool, or protocol used to make a measurement. So if we want to get someone's oxygen uptake, right, we could do a VO2 max test, right? And the type of protocol that we use might be a Bruce protocol, okay? So the test is the means by which you get the measurements. And then once we've gathered all of our measurements, we can evaluate, right? So this is looking at how, or the worth of our data, right? So if we wanted to, like let's go with the Bruce protocol thing, right? We collected everyone's VO2 max measurements, and then we want to compare VO2 max values to other individuals within the same age group, right? So evaluation is comparing different measurements that you've taken. Okay, measurements as a whole give us data, okay? And data is what goes into statistics, okay? If we have a sample, we collect their data, and then we use statistics, which is a mathematical technique, right? That helps us organize and treat the data so that we can interpret it in the context of the research that we're doing, okay? Characteristics of useful data should include these three things, okay? Reliability, which is referring to consistency of measurements, okay? So if we'll have some more examples of this a little bit later on, but the main idea is, can we achieve relatively the same results when applying the same procedures to different test subjects? If you have too much variability within your measurements, that sometimes will point to reliability issues, okay? And like I said, we'll have more examples on how issues in reliability can affect your data or your research design. You also want your data to be valid, right? Or accurate is another way of saying this, okay? And this is just making sure you are, appropriately measuring or using the appropriate equipment to measure what you actually want measured, right? So if we wanted to see how well someone could run a 10K, right, or how fast they could run a 10K, usually we might say like, oh, let's measure their VO2 max and see what their how their oxygen uptake works, right? And then therefore, like continue on and make your assumptions or correlations or whatever you're going to do with that particular data, right? If you want to see how their performance would be in a 10K and you measure their like a bench press, like how much they can bench press, that doesn't really tell us anything about what we actually want measured or what the research question is asking for, okay? So validity is looking at accuracy and appropriateness of your measurements, okay? The last characteristic we want our data to exhibit is objectivity. Okay, this is also known as inter-rater reliability, and it's basically just removing bias from your research design, right? So a lot of times, like we said, we want to, subjectivity is when you have human judgment. You're trying to take out as much human judgment as you can, right? So using machines or software, using stopwatches versus time gates, right? So take as much of your human judgment out as you can. Okay. So now we've had a sample, we've collected data, now we have to classify it. Classification is going to be a huge thing for this class. It is more or less like your starting point for when you're trying to figure out what test to run, essentially. Okay. So we can break it down into two categories, simple categories. There's non-parametric data and parametric data. And a lot of times we'll refer to data within these two compartments, okay? So non-parametric data just means it doesn't meet the assumption of normality. Think normality related to a bell curve, okay? So if we are not able to plot our data in such a way that it creates a bell curve, then we call it non-parametric. If we have parametric data, that means we can meet the assumption of normality, and hopefully this will make more sense when I give you guys examples, okay? So our non-parametric data, or our non-parametric scales, are going to be classified as nominal and ordinal data. For this class, we will pretty much always have nominal data, and I'll talk about that more in a second. But non-parametric scales or non-parametric data are usually more qualitative in nature, meaning that they give you information about the measurements that you've collected, okay? So not always value-oriented type data, okay? Our parametric data or parametric scales are usually more quantitative in nature, so these are where you'll see more numerical value representations of the data, right? So if we have time that we're measuring, or force, or if we're looking at EMG activity and we want the percent of someone's maximal muscle contraction, right? Those would be examples of numerical or quantitative type of data. Okay, and these are broken down into interval and ratio data. For our class, we're pretty much always going to have ratio data. So I highlighted those in red, so you can make stars next to them and say, like, these are pretty much what we're going to use the rest of the semester. Obviously, for this like first section as introductory stuff, you want to know the other two, because we will practice classifying data in a little bit, okay? But first, I want to go over nominal data. This is also known as frequency data. You just have to make sure when you have, or it's also known as categorical data as well, right? You just want to make sure that your categories are mutually exclusive. So that means that one person shouldn't be able to be counted twice, okay? So examples could be, if we're looking at gender, gender would be an example of nominal data, right? You have males and you have females, right? If we're splitting it up into that simple way, at least, right? You could also break it up into ethnic groups, right? Where we have Caucasians, we have Asian people, like, and these are pure, right? Pure Caucasian, pure Asian, pure African American, pure Hispanic. And then if you have one or more of those ethnicities, we would put you in your own category because you are a mixed ethnicity, right? Or a mixed race. So you're mutually exclusive from the other categories in that respect, because you do not solely fit in an Asian category. Like I would be a mix because I'm half Chinese and half white, right? So if I can fit in two categories, it doesn't work. They have to be mutually exclusive. So I create my own category and I'm mixed. Okay. So this would be nominal data, categories. Think categories. Ordinal data is also known as ranked data, right? Usually we have an order to the variables, like if we're looking at positions in a race, like 1st through 10th place, right? So usually there's a designated order, like 1st place comes before 2nd place, which comes before 3rd place, right? But there's no specific quantity of how far apart or how better or worse any score is above another. We just know that's the ranking system that's used for that particular test, right? We could also do this by, or another example would be if we lined up people from shortest to tallest, right? And we numbered those people 1 to 10. We know that number 6 is taller than number 5, but we're not necessarily measuring what that height discrepancy is. Okay, pain scales is another one, or the RPE scale, rate of perceived exertion, right, that we use in VOT max tests if you've ever been put through that horror before. Okay, so anything that has some type of ranked system, but it could be numbers or represented by numbers, but the numbers don't have any value to them other than the actual order that's being described. Okay, so nominal and ordinal data are parametric data. Now we're going, or they're non-parametric, sorry. Now we're going to go into our parametric data, the first example being interval data. I feel like interval data always screws people up. You just have to know there is a no exact, or no absolute zero, right? So if you have a measure of 0, it doesn't mean that you didn't have a measurement, okay? Or it doesn't represent that you have an absence of a measurement. 0 is an actual value on the scale. So examples that the book gives is temperature, right? We know that 0 degrees is an actual temperature, right? And we can go above or below 0 degrees, but 0 degrees doesn't mean that there is an absence of temperature, right? Same thing with sea level. We can be at sea level, which technically in this case would be 0, right? If we're looking in terms of like elevation, right? Or elevation in feet, I guess. Sea level would be 0 feet, right? But it doesn't mean that you're just in non-existent space, right? The other example that's probably more relevant to kinesiology is joint range of motion, right? If you look at this picture, this is a Thomas test, which measures hip flexion or hip flexor mobility, right, or flexibility. And if you have someone who is more flexible, right, usually our horizontal line here is our standard, right, or where we start our measurement, and this person is below 0. Someone who is at 0, right, doesn't mean that they have no hip flexor flexibility at all. It just means that in that particular sense, from our starting point, they're at 0 degrees away from that starting point, right? And we can go above or below that starting point. But the idea with interval data is that 0 does not represent an absence of a measurement, rather it is an actual measured value. Okay, this is different from ratio data, where 0 does represent the absence of a value, right? So usually we cannot have negative values unless a negative is specified as a part of the numerical range we're working with. Okay, so for it might be a little bit too complex, but in like biomechanics, we have this operation of a right-hand rule where negatives actually are translated as directions, right? So in one case, negative values might indicate that you have hip extension versus positive values, which represent that you have hip flexion, right? So negatives in ratio data usually, at least in biomechanics for that example, would represent a direction, okay? But usually ratio data is based on order. So like 0 is the least amount, right? And then numbers going upwards from that are, we know that like 6 is less than 7, right? There's equal distance between your scale points, right? And this can range. So ratio, think fractions, okay? It can range based on the number of decimal points you're willing to work with, etc. Okay. So examples would be weight, height, force, time, right? Like I said, a lot of the data that generally we work with as kinesiologists. Okay. So what I want you guys to do now is just take a couple of minutes to, I'm gonna, yeah, share results. Stop sharing. I don't want to do this anymore. Okay, hold on a second. Oh, poll 2, classifying data. There we go. So you're gonna have a poll. Basically, the poll matches, right, what's on these tables, and I just want you to quickly think what type of data we're working with. I gave you some of these examples already, okay, but a couple minutes to go through these. Pick which one you think, and then go ahead and submit your poll results. And first I have to launch it, sorry. So go ahead and put your results, and then we'll talk about it a little bit. All right, so we're looking at force, right? This would be ratio, right? Because if we had a force of 0, that would mean we'd have an absence of a measurement, right? Or if we had a force plate and the force was 0, we would assume nothing is actually standing on that force plate, right? So in that case, it would be a ratio type data, okay? Because 0 represents an absence of a measurement. For sport, can I scroll on this? Oh no. I'm gonna, That's the other thing, when I like have trouble working stuff, I make sounds, so just like bear with me. I don't think I can have this portion of the screen shared. So hopefully you guys can see the poll results. Can I get like a hand wave or something if someone can actually see? I don't know how I can toggle through that at the same time, but okay, we're good. Great, awesome, thank you. All right, so when we look at sports, that would likely be a type of nominal data, right? If we're categorizing people by, like, if we collected a random sample, how many people play basketball, how many people play baseball, right? We can't necessarily say that it's a rank because we're not saying that one sport is better than another, okay? And ratio data, I don't really think would fit with this, or ratio and interval, because sport, we're not necessarily putting numerical value to it, right? So nominal would be the best answer for this one. If we're looking at sex or gender, almost 100% chose nominal, and that would be correct, right? Because again, we have categories split between male, female, right? Or if we want to expand on that, we could, okay? If we're looking at grade level, most of you said ordinal. This would be correct, right? Because we know grade level progresses in a certain ranking. So we've got, right, kindergarten, then first grade, and then second grade, and then third grade, fourth grade, right? We know that there's a certain ranking that goes along with grade level. VO2, most of you said ratio. Again, VO2, if we had someone who had a VO2 max of 0, that just means we didn't take the measurement, right? So it couldn't be interval because VO2 can kind of only go in one direction, and a VO2 max of 0 would probably mean that if we took the measurement on a person, they're dead, okay? So in this case, it would be ratio, I think, actually. If I, oh yeah, these come up. Haha. All right. I'm so proud of myself. It's the small things, you guys. All right, if we're looking at rate of perceived exertion, right, this would be ordinal. That's one of the examples we gave on the slide, right? Again, someone, you know, could say, I'm at a 7, which is less intense than if you were at a 10, right? So it's, again, a ranking type of system. If we wanted to ask people, are you injured or not? This is kind of like a yes or no question, right? So we're categorizing people based on their injury status, right? So this would be nominal data. Hopefully this is making sense to some of you who chose otherwise, right? If we look at heart rate, this would be ratio data, right? Heart rate of 0, again, means person is dead, which is bad. But, right, 0 is indicative of an absence of a measurement, right? So that's why we have ratio data. And I realize asking you guys these on the fly is kind of rude, but sometimes more learning happens from it, okay? We're looking at temperature. Most of you chose interval, which is the right answer, right? Interval data is when 0 still represents a value on whatever scale you're measuring, right? Same thing with joint range of motion, also interval, which most of you chose, so good job, okay? So classifying data is a big part of this class. You'll definitely want to know how to do that, okay? So let's, oh boy, go away, move on. All right, so how does this play into research design and statistical analysis? Okay, research generally, and I'm kind of going to skim through these because you guys can read a little bit more. Some of it is just like inclusive from the book, okay? But research is the way that we solve problems, right? Either problems that have been unanswered by experts or within a literature field, or maybe the problem has already been solved and you want to challenge it or see if you get similar results using a similar sample or a different sample, right? So once we have a target sample or a target population, we've collected our data, we conduct research to analyze that particular grouping of people or places or things, okay? There's different types of data, or sorry, not data, different types of research. So we have historical research, which is primarily concerned with looking at past events and how those past events might affect other past events, present events, or future problems. And then we also have observational data, which is more descriptive in nature. So a lot of times you'll see this, right, with survey questionnaires that people will answer. Or if, a psychologist wants to take notes from a therapy session or go observe how children, behave in different social settings, right? That would be observational research. What we are primarily concerned with is experimental research, right? It's the process of manipulating different variables and events in order to solve a problem, okay? So the goal essentially is to make a cause and effect inference from the data and the results that we end up getting, okay? And usually, right, if you guys remember the scientific method, we usually start with observations, right, which would be, in our case, in kinesiology, reading the literature, right? And then we come up with a hypothesis. And there's two hypotheses that we're working with. The research hypothesis, which is also known as the alternative hypothesis. And this is basically what prompts the research, right? It's what you believe to be true based on the literature review that you've conducted, okay? And so from that research hypothesis, we have a null hypothesis. And the null hypothesis is what's statistically tested, right? It has to be mutually exclusive to the research hypothesis. And basically it's saying there's no relationship or no differences between the groups that you're testing, okay? So the null hypothesis is like our Debbie Downer hypothesis, where they're just like, you can't prove it, they test you. And you test it. What? Okay. So, what do I mean by mutually exclusive? Sometimes I have jokes. Most of the time, they're not very good. Anyways, if we do an example, we have a research question, right, based on observations. And we want to know what is the difference in driving accuracy between novice golfers and advanced or expert golfers. Okay, so our research hypothesis would say, like, based on observation and other literature review that I've done, right, novice golfers would be expected to not have the same accuracy as expert golfers, right? We would expect them to be different. Therefore, our null hypothesis would say the opposite to that, right, and say that there is no difference between groups, their accuracy would be equal. Okay, so mutually exclusive just means if our null hypothesis says that there is no difference, the research hypothesis would say there is at least some difference. Okay, if we use the same example or the same research question, but we want to add some type of direction to it, right, we could say, based on our literature review, novice golfers should be expected to have a lower accuracy than expert golfers, right? So the null hypothesis, being mutually exclusive, would say there either is no difference between novice and expert golfers, or novice golfers will have a greater accuracy compared to expert golfers. Okay, so just to keep in mind, hypotheses always need to be mutually exclusive. Okay. We'll do a brief intro into p-values, because p-values basically tell us if we have significant differences between the groups that we're comparing or not. Okay, and usually levels of significance or confidence are going to be chosen before you actually run your stats. Okay, so a lot of times you guys will see like 95% confidence interval. That's usually associated with a 5% chance of error, right? Or that's your p-value. It's how much error you're willing to accept. Also, you could refer to it as the probability that you've made an error, right? So the smaller percentage that we have, the better. So usually the p-value is going to be set at 0.05. We'll go over this in future lectures, so don't worry about it. The main takeaway I want you to have from this slide is when to accept or reject the null hypothesis. So remember, when we run all of our data through statistics, we're technically testing the null hypothesis. Okay, so if our p-value ends up being less than the amount of error we were willing to accept, that means we probably made or had a probability that we made a small amount of error. Therefore, we reject the null hypothesis and we say, I have proven that, you know, there is a difference between my groups, or there is, like, novice golfers do indeed have a lower accuracy than expert golfers. Okay. If we have a high percentage of error, or a probability that we made, or if we have a probability we have a higher percentage of error, usually we just go ahead and accept the null hypothesis, right? It's a innocent until proven guilty type of thing. So the null hypothesis is always going to be correct unless you have a small probability of error that you, or small probability that you made an error, right? So p-value less than whatever your set level of error is going to be, usually we reject the null. If you have high probability of error, we usually accept the null. Okay. So I give you guys an example of this using that golfing scenario. Okay, so I'll let you review that just as an indication of what p-values mean. I feel like a lot of times if I overtalk this one, I just end up confusing people. So if you have questions on it, please ask. Okay, and we are running short on time. I was a little bit overly confident, I suppose. So if you want to stay in when it turns like 6:50, or that's 6:50 my time, sorry. When it turns to 3:50, if you want to take off, that's fine. If not, I'll continue the lecture and you just watch whatever is left in the recording, okay? So yeah, go ahead and look at this example. But I want to talk about independent versus dependent variables, because this is going to be relevant information for your activity this week. Okay, most of you know what independent and dependent variables are, so I'll just briefly skim over this. Okay, your independent variable is usually a variable that is controlled by the researcher, right? So if you are categorizing different sports and you're measuring vertical jump and you want to know how sport participation has an effect on vertical jump height, right? You're controlling the sports that you collect. So let's say you have basketball, you have volleyball, and you have football players. I don't know. I'm just making this up as I go. Okay. So you are essentially controlling the sports that you're choosing. Okay. This is also known as an X variable. Independent variables are usually plotted on the X axis because they are X variables, right? And usually independent variables are represented in levels. So the example I just gave, our independent variable of sport, which is what we are actually controlling, right, would have 3 levels, right, based on the types or numbers of categories that I have. So I had basketball, volleyball, and football, right? The dependent variable is what we're actually measuring. So in this scenario, we wanted to know how sport affects vertical jump height, right? So vertical jump height is what we're actually measuring. Therefore, it is the dependent variable, right? It's dependent on whatever you're controlling, okay? So usually the dependent variable is known as the Y variable and is typically plotted on the X axis, okay? So generally when you're reading research and there's a research question or a title of a research paper, a lot of times it'll say, like in this scenario that I use, right, the effect of sport involvement on vertical jump height, right, or the effect of the type of sport played on vertical jump height, right, usually is formulated in the effect of whatever the independent variable is on what is actually measured, which is the dependent variable. So I've included some practice scenarios for you guys that you can go through. And then obviously we can, bring these up as points of discussion if you have any questions. They're meant to be a little bit open-ended. So it's kind of open to your interpretation. Okay. So the first scenario that I gave you guys is the effect of time spent in practice on sport performance. Okay. So I give you guys what the actual independent and dependent variables are, and then it's up to you to figure out which variables would go on the X and Y axis based on how they are identified in that example, right? And then what type of data our measurements would classify as, okay? So what I'll do, because I want you guys to, this is good practice for classifying data, start off when you go back through your lecture notes and you're practicing, like this is a scenario, because a lot of times in the exams I'll ask you, like break down your information. What's your independent variable? What's your dependent variable? What type of data is it? This is kind of like the basis of and the foundation of how you're going to figure out what statistical tests you'll run in the future. Okay, so go back through, make sure you can double check if your independent and dependent variable choices were correct. Right? And then answer these questions. I'll post the answers on Beachboard later in the week so you can double check your work. And then obviously if you guys have questions after that, let me know. Okay. I'll probably post them in the discussion board since everybody should have access to that. So just check in that area when you feel confident in your answers. Okay. There's another example of the effect of diet on weight loss or weight gain. So you just think weight change in general, right? So again, go through this, identify independent, dependent variable, which ones would go on the X or Y axis if you were plotting them, and then what types of data you would classify those variables as, okay? Our time is technically up, so if you have to leave, totally fine. Okay, if you want to stay in, we are kind of wrapping up here soon. Okay, I'm going to guess about 10 or 15 minutes more. Sorry. Like I said, this was usually in an hour and 50 minutes, so I'm not used to having to rush it as quickly. Okay, so you can go through, practice this example. Again, independent and dependent variables have been identified, so you can check your answer. And then, again, I'll post the answers in the discussion board later in the week. Okay. So the last thing I wanted to talk about today is the quality of research, right? You have a sample, you collected your data, we know how we're processing it, kind of, based on the types of variables that we have, right? So now it's just double checking. You have this map laid out of how you want your research design, but we have to make sure that that research design is sound in its design, right? So the first thing that we're going to talk about as far as quality of research is internal validity. And you guessed it, if there's an internal validity, there has to be an external validity. But internal validity is a little bit more broad in the different examples that we can give, just because this is the design of the study itself. Okay, so the definition given by the book is the measure of control within the experiment that ensures results are due to the actual treatment applied. So our goal is to maximize internal validity. Okay, if we want to maximize it, in order to control it better, we need to know what actually reduces it. And we're going to go over each of these 4 things in the next slides. Okay, and these are just 4 major categories that the book has identified. It by no means is a comprehensive list of things that could reduce internal validity. Okay, so the first thing that we'll talk about is learning or exposure effects, right? Usually observable when you have some type of pre-test or post-test, right? Or if you're having somebody do multiple actions of a trial. So usually we would control for this effect by having inclusion of control groups, right? So if we've got, let's keep the golf example, right? We're actually measuring maybe putting accuracy of novice versus expert golfers, right? And novice golfers obviously wouldn't have a whole lot of experience. So whatever our treatment is, say we're giving them feedback, right, to help or to see how much they're retaining from the feedback that we give them. Already we're imposing a learning effect, right? But if they're new to the actual task of putting, right, we don't know how much of the learning effect we're trying to get, right? We don't know how much of that is actually coming from the treatment versus coming from the fact that these people haven't really had a lot of experience playing, okay? So what we would do is we'd say, oh, here's a control group who has never played a day of golf in their life, not even mini golf, which is kind of hard to believe because mini golf is really fun. But we would have a control group that has 0 experience in golf, and then we would use that as our normalizing factor, right? To say the observations we saw between novice and expert putters, right? We would be able to compare them to the control group and say, well, this was the degree that happened for the control group, so that must be the relative learning effect that we should take out of what we observed in the other groups, okay? It also could be that you throw in maybe not control group, sorry, that was my example. Maybe not that you throw in a control group, but that you add in practice trials. So if let's say we're keeping the golf thing and we have a specific task that we want somebody to participate in, right? We could say, okay, all of our golfers are going to have 5 practice putts before they start, and that should kind of eliminate the learning effect that we would expect them to have due to exposure to the actual task. Okay, you can also cut this down and say we're going to have people do 5 trials of the treatment, but we're only going to analyze the middle 3, right? So the first one would be canceled out because it's like that's the first time they're trying it, and then we would cancel out the 5th observation because we would say that's the one they have the most experience on. So the greatest or most valid capture of the actual effect that we're measuring would be in those middle trials, okay? So those are examples of how we can control learning effects and why they could be detrimental to your design. Okay. We also have intervening or extraneous variables. So these are variables that directly affect the results of your dependent variable that is measured, but aren't actually supposed to be included in the study. Okay. These should be controlled for as much as you can, and it's usually going to be in your inclusion and exclusion criteria. So an example that I'll give is if we were measuring muscle activity, usually we would give a person an MVIC test for kind of like our normalizing factor. So we can say, oh, you were working at 50% of your maximal contraction effort. Okay. So intervening variables that could affect MVIC testing could be if, somebody just did a leg workout the day before, right? Because delayed muscle soreness, or that's a real thing, right? So say they do a big leg day 24 hours prior to MVIC testing, and you're actually testing maximal effort on sore muscles, right? That's going to interfere with the data you collect. Okay, so making sure that you let your participants know, like, don't do leg day 24 hours or at least 24 to 48 hours prior to your testing time would be an important thing, so that your data is not being skewed because of fatigue, right? If you give a post-test too soon after treatment, that could also affect, right, if the results. So if we're looking at retention, right, everybody has taken motor control, I know this, okay, or motor control and learning with Dr. Wu, right? So if you have a retention time, let's say you give a 1-day retention test, a lot of times you won't see a whole lot of difference between that 1-day retention test data and like post-treatment data, right? Or if you give them their last assessment, okay? Versus if we look at retention after a week, okay? Sometimes it could be a fatigue factor playing into timing with regards to a post-test. So maybe you had somebody do a whole bunch of maximal exertions and you don't give them enough time to rest before actually seeing if the treatment worked, okay? Next example would be healthy participants and no previous injuries. This is often a very common description of people who are included in a study, right? So we have like healthy males and females between the ages of 18 and 30 who have, if like previous injuries, maybe it has an effect on your data, maybe it doesn't. A lot of times that's something I will include, especially if I'm looking at movement analysis, just because we know that tissues don't always heal back to their original states, right? And it could inhibit movement, maybe not always in a drastic way, but it might inhibit movement in some sort of way that's different from someone who hasn't had an injury in that area before, okay? We also know injuries can cause people to make compensatory actions, right? So a lot of times we might say, oh, make sure like you're healthy and you haven't sustained a lower extremity injury within the last 3 months. Just an example, okay? So again, inclusion and exclusion criteria, this is kind of where you sort out who your sample is going to be so that you eliminate as many intervening variables as possible, okay? Another example would be if you're comparing diets, right, to the and their effectiveness on weight loss, right? You want to make sure, if you're solely looking at diet, maybe you say we have all sedentary people, so you know that physical activity isn't really playing a role in the weight loss that you might observe, okay? Or you might control the BMI target of your sample. So let's say we want only people who have a BMI of 30 or more, right? So we want to look at weight loss strategies for obese people, right? Because people who are further away from their ideal weight tend to lose faster than people who are closer, okay? So we can see how that might intervene with the results that we would get from a study with that particular scenario, okay? Two last things that are pretty intuitive are, at least in the explanation of how they work, are instrument error, okay? And then the last one is investigator error. So instrument error is usually just due to instrumentation or equipment failing on you, okay? Or it wasn't used properly, okay? So examples could be measurements of force, or easiest way you guys can think about this is if you have a bathroom scale at home, usually there's a 0 or a tare function on the scale, right? So that you know you're starting at 0, meaning there's an absence of a measurement, right? Or an absence of a body on the scale. And then when you step on it, right, it's been calibrated so that when you step on, you actually have an accurate measurement of your weight or the amount of force that you're placing on a force plate, okay? With 3D motion capture, usually we calibrate the system based on an L frame, right, to establish our global coordinate system. And on that L frame, we have certain reflective markers that are a certain distance from each other. That way, when we have a person with reflective markers step into the system, we have a relative idea of how far apart those markers are based on the frame that we use to calibrate, okay? Range of motion testing, if you're using an inclinometer, specifically a bubble inclinometer, it's like a little circle, and then there's liquid within the circle, and then there's like a measurement dial that you can turn, such that you can, keep track of wherever the bubble ends up is the degree of the range of motion that you're testing, okay? So when we're using something like that, we have to make sure the bubble starts at 0. That way we have an accurate measure of the degree of the range that we're measuring, okay? So instrument error, I feel like that one is pretty easily understood as far as examples go, usually, okay? Investigator is the last thing that can negatively affect internal validity. So this is usually when an investigator will insert their own bias or judgment within either the collection of the data or within the analysis of the data. Sometimes it's intentional, which would be bad, okay? Other times it's unintentional, which is just something we have to be more aware of, especially if we're the ones collecting the data, right? Error could be due to reading measurements incorrectly. So let's say somebody was doing a vertical jump and you're using a vertex and you misread how many bars they ticked off, right? Maybe you're off by a quarter or a half an inch, but that might mean the difference in the end when you analyze your data, right? So error in reading measurements could be one thing. Maybe you get your numbers backwards when you record them down on a paper or computer, okay? It could also be tester-to-tester reliability. So at least when I have a group of research students, I try to make sure that everyone is well-versed in the procedures that we're doing to make sure that anytime any one of them is testing the subjects we're working with, I know that the test is being administered the same way, right? Because one of the qualities or characteristics of good data is reliability or consistency, okay? We could also have investigator error when we insert bias into judging skills, right? So having a personal evaluation would be a way that this could work, or that we could insert bias versus using like a standardized criteria or a standardized test, right? So generally this is why we, teachers at least, usually use grading rubrics. So that way they're not biased by, let's say they had like an altercation with a student, that altercation shouldn't bias that student's work if that work is being based off of standardized criteria, which is described in the grading rubric. Okay. Lack of experience using the equipment. Again, this kind of points back to tester-to-tester reliability, or just reliability of the tester in general. Okay. And then we also have investigator error when we intentionally falsify data. This is not good. You can do this in a couple of ways, not that I'm encouraging anyone, but you can adjust data values to match what is desirable in your eyes, which is not true because it's not real data anymore, okay? or if you use different methods to collect or analyze for different subjects, okay? Unless it's warranted, you should treat every subject equally because they have all been equally chosen, at least randomly, right, from a particular population. So if you start adjusting how you treat individuals that's not outlined in the research design, you start inserting bias into your results, which then makes them not as credible, okay? Lastly, we're going to talk about external validity, okay? I know you guys are hanging in there. I really appreciate it, okay? External validity is different from internal validity such that it's looking at the generalizability of the results that we've collected. So internal validity is looking at the actual design itself, the innards, right, of how we create the design. External validity, we just want to make sure that the sample we're measuring and the information we get from that sample can be inferred upon the population from which it was taken from, okay? And we term this statistical inference, and we'll have a whole lecture just based on that in a couple of weeks, okay? But examples of how we can control external validity is lab research, right? It's a great method to use because we can control our environment, we control who our subjects are. The downside to using lab research is sometimes our environment becomes too controlled and it doesn't mimic, you know, what real world situations might express, okay? So kind of have to take that into consideration. Controlling your study design is really good, but it can also hurt you if you control it too much, because then you start decreasing how generalizable your results are to the population, okay? Sample characteristics can also affect external validity. So again, it's good to be specific in your inclusion-exclusion criteria for who can be in your sample, right? But again, if you're too limiting, then you can't generalize to a larger population. So, I mean, if we're only interested in basketball players, or like, let's say female basketball players from the age of 10 to 15, right? That's not too limiting, but based on other characteristics you add in, like, oh, they have to be healthy, they have to not have sustained an injury within a certain period of time, they have to have at least X number of hours of recreational basketball a week, or they have to participate in a club sports team, right? The criteria that you impose starts to eventually limit how generalizable your sample data would be to a larger population. So it's just something to keep in mind. Intervening variables, same examples that we had used previously, right? Things that can affect your study design without actually being included in your study design can also affect external validity, okay? So the challenge to you as a researcher is to try to balance internal validity and external validity, and then be able to identify the limitations to the study that weren't controlled for, because sometimes you can't control everything, okay? All right, misuse of statistics. This is the last slide. We're almost done, okay? Misuse could be inaccurately presenting results or misleading people to think that your results mean something that they don't actually mean. A lot of times this is either due to small or non-random samples. So the bigger your sample size can be, the better, because that means you have a greater representation of your population, right? You could have inaccurate results because you have inadequate operational definitions. And operational definitions are simply the language that you use, right, in your inclusion or exclusion criteria. It could be a good example that I like to use, at least for this one, is when you see like Frozen 2, the #1 movie in America. And then you're like ever? Like the actual best movie in America? Or is it the best movie in America in animated films that are currently in theaters right now, right? So if you don't accurately define what you mean by the #1 movie in America, then your results could be misleading to people who are reading them. Okay. We also have the presence of outliers, and we'll talk about the semi soon, I think in 2 or 3 weeks. Outliers can skew data quite a bit. We'll actually talk about outliers next class, so that'll be fun. But the whole point of research is to make sure that we are collecting a sample that is as representative of our population as possible, and then we're accurately measuring that and then presenting it to the world. Okay. So it's the responsibility of you as researchers to report well-documented, valid, reliable, and objective results. Okay. This includes data not only collected and analyzed, but also data and information reported from other sources. So making sure you have reliable sources that you are obtaining from review of literature. Okay. And then also checking the credibility of sources that lead to your research question, right? It's not like you would make a research question off of something you read on Wikipedia, right? You'd probably take a culmination of a whole bunch of literature from PubMed or, peer-reviewed articles, and then make a hypothesis or a research question off of that, right? Because those are considered credible resources, right? So hopefully this was a nice introduction. I'm sorry we went over time, but hopefully you guys got something from that. I will post the recording probably soon once I figure out how to do it. And then does anyone have any questions before we take off?
Hey, Professor Wong.
Ha!
I had a quick question, but I can ask you at the end. It's just concerning myself adding into the class. And
Oh,
I saw you
yeah.
respond to my email, but I just want to let you know also, this class was only meant for exercise science majors in kinesiology, and I'm a sports psychology. So I was hoping that maybe that's why I didn't get in the first time.
Possible.
Yeah, so I just want to let you know that, and hopefully that doesn't stop me from taking this class.
No worries. We'll get you in. It won't stop because there's room to add.
Awesome. Thank you so much.
Yeah.
Besides that's it for me.
Okay. And also, just because there was that example just now, you guys can call me Natalie or Nat. I technically don't have the title of professor on the campus just because of the part-time lecturer position that I'm in. So you can call me by first name basis, is all good. But if you guys have questions you want to stay in and ask, I'll stay in for probably another 5 minutes. If not, you guys are free to go.
Hi, Ned. I have a question. We do have to use scientific calculator in this one, right? TI?
No. A lot of your calculations will be done through Excel or SPSS. If you want to have a calculator nearby, that's okay, but pretty much any calculation you can do on a scientific calculator can be done in Excel.
Okay, and when are we meeting up next? Is it the same Wednesday time or Monday is the only time? I came in late because...
Oh, no, that's okay. We'll meet on Mondays at 3. Pretty much every week. You can refer to the course syllabus that's posted in Beachboard for the days or the weeks that we'll have lectures. And then the only weeks that we won't have meetings on Mondays will be exam weeks. That'll be like a modified meeting time for anyone to ask clarification questions. But yeah, other than that, just Mondays at 3. Okay. And then activities will be pre-recorded and posted.
Okay, so we have activity class 2. Is it more physical or it's more like I have to do like work on paper?
No, it's more work online. Okay. So I posted that video in the media section. And like I said before, this class used to be an hour and 50 minutes. So I think the activity for this week is like an hour and 40 minutes. because
Okay.
it usually fits within the time that I was allotted previously. So that's just recorded. You have a Excel data sheet and instructions and questions you have to answer. But I go through it with you guys step by step, so it should be okay. But that one you just follow along as you watch the video.
Okay. All right. And that's it for me.
All right. Anyone else have questions? No? All right. Well, I'm going to close the meeting. Feel free to email me if you have anything pop up.